Yeah, so a couple of words about me. I worked in Huawei Research Institute and in Yandex, and now I've been working in Perplexity AI for half a year. And I'm going to talk about the stages of the LLM training, and mainly the last stage called post-training or reinforcement learning from human feedback, and the recent advances in that field, and also share some of the experience Perplexity had applying this to real-world tasks. So let me first gauge the kind of technical knowledge of the audience a bit. So raise your hands if you know how LLMs work. Okay, not bad. I think I could argue that nobody really knows how LLMs work, really, but jokes aside, like who has a rough idea how reinforcement learning works? Okay, nice. And who knows how like GRPO and verifiable rewards work? Good. Okay, and who has seen a blog post from Perplexity AI about applying like GRPO to mathematical problems and stuff? Okay. Hopefully no one. Okay, yeah, as you can guess, those are the topics that I'm going to talk about. So let's start with the intro. So yeah, what are LLMs? So LLMs are large language models, and language modeling means that we just model the language as a sequence of tokens or words, and we just predict the next token. And because it's not like defined deterministically, we predict the probabilities of next words. Like deep learning is very, well, probably powerful, maybe innovative, but not so probable that it's limited. So deep learning is unlimited. And we take some model like a neural network to predict those probabilities. We can sample the next word, add it to the existing sequence, sample the next word, and so on, and we can generate texts. And the first letter L is large because current day neural networks that do this task tend to be very large. Great, so what are the stages that you need to come through to get your LLM? So yeah, this is a great meme illustrating the 3 stages. So the first one is unsupervised learning, when you have this like powerful model who already has all of the knowledge, but is kind of cursed and not really useful. Then you polish it with supervised fine-tuning, and now it looks kind of like human, and you can chat with it. But then you can make something even shinier and prettier and better if you apply reinforcement learning from human feedback, or RLHF, and that's the main character in today's talk. So a couple of words about the previous stages. So in pre-training, you just scrape like the whole internet. You find as much text as you want. As we remember from the previous day, of course, the data quality still helps, so you'd better clean your data, but you do not need any human markup, any human labels. Like you can just take random text from the internet, random books, and you can train your LLM to just predict the next word in those texts. You do not need any special human annotation. And this is cool because yeah, to collect this data is quite cheap, but it's really expensive because to really build a competitive frontier model, you now need like hundreds of thousands of GPUs, and so only like a handful of companies or startups can afford to do that. And also the LLM that you get in the end, well, it's just trained to continue random text from the internet. For example, if you ask it a question, like what is the capital of France, it may answer you with more questions. Because, well, it's reasonable to assume if there is one question on a random internet page, there might be more questions. So it's kind of likely that after one question, more questions would follow. And so, yeah, you get an answer that is like plausible, but not helpful at all. And so, yeah, to make this LLM actually useful, to make it solve the tasks you want it to solve, you need to do some later training stages. So the most straightforward one is supervised fine-tuning. You just collect the data of demonstrations of the correct answers or the correct like chat format you want your model to adhere to, and you train the model to produce those outputs. On the plus side, this is like ground truth demonstration. If you have high quality data, maybe your model will really understand exactly what it needs to do. But on the flip side, it's really expensive to collect this kind of data because you need the humans to write a lot of text to demonstrate the correct behavior, and writing text, especially high quality text, is quite expensive. Also, like you might want different qualities from your LLM. Like maybe you want it to be helpful, but also like harmless and honest. And if you collect a huge data set and then decide that, I want my data to be a little bit more honest and a little bit less helpful, then you need to maybe rewrite like half of your data, which is, again, expensive. And also, you cannot really expect your LLM to be better than the data that you put in, because it's just trained to copy the behavior that you show to it. But it will learn the formats of the kind of communication that you want it to adhere to. For example, if you ask it a question, now you can expect that it will actually answer your question. So the last stage that is currently employed is called reinforcement learning from human feedback. And so a couple of words about what reinforcement learning actually is. So in like vanilla supervised training, you have some inputs, a model, and the model outputs, and you have some like ground truth outputs. You compute some loss that's differentiable, and you can tweak the model parameters to minimize this loss. But the kind of framing of the reinforcement learning is much broader. In it, you have some environment, you have some agent that takes some actions in that environment, and it changes the states, and sometimes it gets some reward. For example, you can imagine an agent that plays chess. So the actions would be different chess moves, and after a sequence of moves, when the game ends, you get like either +1 reward if you win or -1 reward if you lose. And so now it's much harder to figure out which actions are good and which actions are bad. It's much trickier to tweak the model to be better, because like after a huge sequence of actions, whether you win or lose, it's not really clear like which exact actions led you to winning or losing. And also the reward that you get may not be differentiable. Like it's hard to flow the gradients through this like discrete feedback of either you won or you lost. So reinforcement learning can deal with that, but it's not like magic, and you have to pay something to like do this non-differentiable task. And usually in reinforcement learning, the training process is quite unstable. So how does that apply to the LLMs? So in LLMs, we can view the tokens, the words that the LLM is generating, as actions. And when the output from the LLM is finished, we can call a human and ask him to judge if that output is good or bad. And we can view that as a reward. And so now we can try to train the LLM to maximize this reward. So to produce the outputs that will be liked by humans. And this is great because we can capture like what the humans actually want from the LLM, like which behaviors they like, which behavior they do not like, and we can align kind of the values or the behavior of the LLMs with the kind of values or wants of humans. So theoretically, this is really great. In practice, this is very hard. If you come to AGI, this is exponentially harder and very hard problem. Would be nice if more people worked on it. But in practice, if you just, like, for example, want your model to refuse some behaviors, or you want it to solve mathematical problems better, this works quite well. So why is this better than doing supervised fine-tuning? Well, now you need from humans not to demonstrate the behavior, but to judge the behavior of an LLM, to just say, like, this output is good, this output is bad. And it's much easier for a human to do than to generate a perfect example of the correct answer. Also, if the LLM is trained and given feedback during the training, then it can kind of try different strategies of the outputs and see which ones work, which ones do not. For example, it can try to do different strategies in the chains of thoughts, like modern reasoning models can do different like reasoning and reflection traces, and maybe during the training they will find the kind of reasoning that leads to correct answers, and that will be reinforced by this reinforcement learning. But unfortunately, if you have to ask the human to rate like each answer of your LLM during the training, this is still not scalable because we want to train in an automated manner, we want to do like multiple iterations per second maybe, and it's not feasible to ask humans to rate that many answers. So we need to replace humans with machines. And now we come to reward modeling. So we need something that can kind of infer faster and more efficient than a human. So we will kind of distill the human feedback into a model. So this could be done like, let's ask the humans to rate the answers like from 1 to 5 and then just train a regression model, but there is actually a better way to do this. So we can collect pairwise preference data. So we take one input for the LLM, we sample multiple outputs or continuations, we take like 2 of them that are different and ask a human to judge which one is better. And so we have a data set of like winning and losing continuations to the same prompt. And then we train a model to attribute high scores to the winning continuations and low scores to the losing continuations. And then we can use the output of that model as a proxy for the human reward and use it as a signal that the LLM will train to maximize. So why is this pairwise data better than kind of scalar regression data? Well, you could argue that you can capture more nuance. Like if you have only like from 1 to 5 ratings, that is not really granular. But if you can compare any 2 texts that are less subtly different, then you can catch more nuance in their differences. Also, maybe something that is 3 for one human can be 4 for another, and you have to kind of calibrate those scales of marks. And with pairwise training, it's easier because like maybe the humans will agree more on which one of the 2 answers is better. But this is not perfect. The first kind of disadvantage is that the absolute value of this reward doesn't really make sense because it's only trained to compare 2 answers and never like one answer in isolation. You have to keep that in mind sometimes. And also, because we replace the human with machines, and this is an imperfect process, if we now try really, really hard to optimize this reward model's reward, we may overfit. Like maybe the LLM will train to output some gibberish, some like adversarial attack on this reward model to maximize the reward, but the actual answer will not be useful because the reward model is imperfect. So we have to keep that also in mind and do some regularization. Also, if you want to do this even cheaper, you can replace the human with like ChatGPT even on this stage. So you can collect this preference data from some frontier LLM, like ask OpenAI API, please rate those 2 answers, like tell me which one is better. And then you can distill it into a smaller model that you can infer scalably during training. And this is much cheaper, and it's, again, easier to recollect the data if you decided that you need some other features. But, of course, the quality might be lower, but for some like easy cases, this might be OK. So let's sum it up. For the reinforcement learning to work, you need some base model that you're going to train. This can be the SFT model or the pre-training base model. You need some reward, some signal that the LLM will train to maximize. And this usually comes either from the trained reward model or from hard-coded functions. We'll get to that later. And you need the RL algorithm that will actually train the model to maximize the reward. And that's what we're going to talk about now. So there are different kind of optimizer, different algorithms you could do to do this. And the simplest one that is actually not really famous and not often talked about is rejection sampling, aka poor man's RL. So the idea is like really simple. You take one input again and sample multiple completions, like 10, and you score them with your reward and you pick the best one. And this like elite top 1 completion is probably better than the average one because you took like 10 tries and picked the best one. And so now you can use those top 1 completions as data for the SFT. Because like, for example, maybe you want your LLM answers to be less toxic, and out of like 10 completions, some will be a little bit more toxic, some will be a little bit less toxic. You'll pick like the least toxic answers, and when you fine tune on them, maybe your model now will be less toxic. And like you don't really need any RL infrastructure for this. You just need to be able to get answers from your model, and you need to be able to train your model in an SFT manner. And this is really easy and like implement it everywhere. So this could be a like good first step to, as a sanity check, to check that your reward model works. You can do this and see like how the LLM answers change. If they change in the directions you really want them to, then you can proceed to some more aggressive types of RL training. And now we come to PPO. This is kind of the industry standard because that's what like OpenAI guys did to first they arrived to Instruct GPT and then to Chat GPT. I think it was also used to train Llama 2. And this is an algorithm that came from the kind of vanilla area of reinforcement learning. And as I said, reinforcement learning training is quite unstable, so it can take like a lot of moving parts and a lot of kind of duct tape to stitch it all together and make it stable. So maybe this is not really optimized for LLMs, but this is a powerful algorithm from the reinforcement learning. So let's briefly describe how it works and what are the moving parts. So you have your policy model, that's the LLM that you are going to train. You have some inputs and sample and output from that policy model. Then you can score that model with your reward model to judge how good it is. And also you score it with the reference model. This is kind of the frozen checkpoint that you started with. So as we described, if we optimize the reward really, really hard, we may produce some gibberish or adversarial examples. And so we regularize our model not to stray too far from the initial model. So we see how like different those predictions of our current policy model are from the reference model that is frozen. And if they are too far apart, we penalize it. So this is just for regularization. And also a new moving part is the value model. As I've described previously, like when you sample multiple actions or multiple tokens from the LLM, you get some reward score that you want to optimize, but you don't really know like which of those tokens are good tokens and which of those tokens are bad tokens. And so this value model and advantage estimation helps you to kind of smear that reward, that's like one signal to all of the tokens to see like which tokens contributed to this answer being a good answer. And of course, this is also a model. This is like we don't actually have this feedback. We only approximate it with some learned model. So this is, again, not perfect. But it helps kind of better optimize each token output. And so, yeah, there is also a very complicated loss. And I spared you from looking at the loss formula. It also has a lot of hacks. But as a result, this thing optimizes the reward quite well and is kind of sample efficient. And so you can get good models like ChatGPT from it. So what are some more modern and easier approaches? Also, I guess you could also call it an industry standard, is DPO. So this is a clever algorithm that bypasses training the reward model. So we have our preference data, so the pairs of winning answer and losing answer, and we do not train a reward model to approximate the human judgments. We can directly train of those pairs of a good answer and bad answer. This is actually kind of really similar to the SFT. It just has two parts. Like the first term contains the probability of the winning answer, and we want to maximize it. And the second term with the minus sign contains the probability of the losing answer, and we want to minimize it. So this is kind of like training on the good answers and untraining on the bad answers. And there is some like clever loss formula that you can theoretically prove that it's doing something similar to the PPO if you first did the reward modeling and then applied this. So this is...
Sorry, what is sigma and sigmoid?
Yeah, it's the sigmoid function. Yeah, and again, this is easier because you don't need like this value model, you don't need the reward model. You can just train on those pairs of winning answer and a losing answer. So it's much better, again, from the like infrastructure point of view, because you don't need to keep all of those like 4 models in your GPUs. And I think it was used at least as one of the stages in Llama 3 training and in Qwen 2.5. Also, as a bonus slide, you can kind of still do DPO if you have a reward model. So if you have a reward model and you can score different outputs, you can sample multiple of them and pick a very good answer and a very bad answer, and use those as a like winning and losing answer for the DPO. And this lets you iterate, because you can like collect this data from your starting model, you can train it with DPO, then you can collect new data from the obtained model and do another iteration of this DPO. And this is closer to like online reinforcement learning, because in PPO, you actually score the answers that are produced by the model that you are training right now. But in DPO, you have pre-collected data set of answers, and so this is not really online training. But in like iterated DPO, this is kind of in the middle of those two. Next, we come to reinforce leave one out. This is from Cohere, from a paper, reinforce leave one out. This is an algorithm that is can be viewed as a simplification of PPO. So again, you have multiple tokens, you have only one reward for them, and in PPO you try to smear that reward on all of the tokens and to train your LLM. And you need a special value model to estimate those reward scores. Well, what RLOO does is the following. Again, it takes one prompt and generates multiple completions per prompt. And then we can score them with the reward model, and we can see which completions are above average on the rewards and which completions are below average. And we can, again, maximize the probability of generating those above average completions and minimize the probability of generating the losing below average completions. So this is better than rejection sampling or DPO with the reward model, because we are not only picking the best one or the best one and the worst one. We are using all of the completions to train our model. So this becomes more sample efficient. And again, you do not need that special value model that you needed in PPO. Okay, now we come to some new shiny stuff called reinforcement learning with verifiable rewards. It's an observation that we do not actually need human feedback for all of the problems. Sometimes, for example, we have some formatting constraints. We want our answer to be less than 1024 tokens, or we want our answer to be a valid JSON file. And we can check it with some Python code. We do not need humans. We don't need to ask humans to rate it. It's an objective thing that you can just check with a deterministic function. And also, if you have a mathematical problem and you know the correct answer, you can judge whether the LLM's answer is correct or not. And if you want your LLM to write some code, you can then launch that code and see if it compiles and runs and if it passes tests. So yeah, this is an objective way to get rewards without using humans. And we can use it in reinforcement learning. So one of the examples is Meta's, from the Meta's Perfect Blends paper. The method is called CGPO. And it puts together a lot of different training signals. So you can have reward models, as we discussed earlier, but also you can have those binary judges. For example, does the length exceed the length limit, or is the answer for a mathematical problem objectively correct or not, and so on. And so you can have different data sets. You can have answers for all of those prompts. Again, you sample multiple completions, and you pick good completions and bad completions from them. Good completions are the ones that pass all of those binary judges and binary filters, like correct answers, correct formatting, and so on. And the bad answers are either those that do not pass some of the filters or the ones that obtain low reward from the reward model. And again, you maximize the probability of the good ones, minimize the probability of the bad ones, and you can put this all together to obtain the model that is simultaneously good in mathematics, good in coding, it refuses harmful prompts, and just outputs something that is liked by humans. This is a lot of hyperparameters to tune if you want to combine this all into one signal, but yeah, you can do it. And now we come to GRPO. This is a very famous algorithm because it was used by DeepSeek to train their R1 and R10 models. And yeah, it's not really that much different from the algorithms that we already discussed. So again, in PPO, you have a lot of those moving parts, the value model and the advantage estimation. We can get rid of that, again, by using the group calculation. So again, we sample multiple completions per one prompt, and we can see which completions are kind of above average and below average. So we can kind of compute the difference between the rewards of a single example and the average reward to see how good it is compared to the average one. And we can use that as advantage without needing this special value model to estimate it. And we can plug this into the PPO loss. So they basically just copied that huge scary formula from PPO paper and used it in GRPO with this group advantage calculation. And it worked quite well. They were able to train their DeepSeek. But as this algorithm is quite new, it's not really fine-tuned to its perfect state. There are still papers that are coming out today that actually tweak some of those parts to make the algorithm more stable, maybe more sample efficient and all that. For example, the papers called DAPO and GRPO done right. Okay, great. Yeah, I think we can skip those details and go to the takeaways. So reinforcement learning from verifiable rewards works if you have verifiable answers. Like you have some objective way to tell if the answer is correct or not, if it adheres to some filters or not. And for the kind of problems that have this feedback that you can get not from humans but from like code, you can expect a lot of progress in AI because it's easy to optimize the performance of the LLMs on those kind of tasks in a scalable way because you do not need human markup. And also, when we train the LLMs to be successful in, for example, mathematical tasks, we can also train them to reason in a good way, as I've already mentioned. Like maybe they can find how exactly they need to chain those reasoning steps to arrive at a correct answer, and that can be explored during the reinforcement learning by the model and reinforced or learned by this training algorithm. And this allows those things like ChatGPT O1 and different O series, not for all, to do inference time scaling. Great. And finally, I'd like to share some of the experience that my colleagues from the post-training team in Perplexity AI had when they tried to apply this GRPO to DeepSeek models or Llama models to solve some mathematical tasks. And we hope that this will teach us how to do like modern reinforcement learning, and then we can actually apply it to our in-house models to produce better answers for the like retrieval augmented generation. So the first kind of challenge that we faced is we needed to pick the framework in which to implement those RL algorithms. And historically, we used the NeMo aligner framework that's done by NVIDIA. And it's quite good because it has a ton of optimizations, like tensor parallelism, like sequence parallelism, data parallelism, those like 4D parallelisms that can really make you leverage those GPU resources to train huge LLMs very efficiently. But on the flip side, this framework is quite large and hard to maintain because it's like PyTorch, then Torch Lightning, then like Megatron, then NeMo Aligner, and you have all of those layers and complexity, so it's hard to implement something new or to maintain code. You have like 3 different repositories that you need to commit to implement one change. So we tried to find some framework that would be more lightweight, and we like the Torch Tune framework the best. It's much closer to the native Torch, and it also already has some reinforcement learning algorithm implemented. And so, yeah, historically we used NeMo Aligner, but we are kind of transitioning to Torch Tune now. So to implement GRPO, our colleagues faced a lot of technical challenges and did some like polishes and improvements on the existing code base. So for example, that like KL divergence term that you need for regularization, there are better estimators that you can use to do that, and that can increase the kind of effectiveness of this regularization. Also, because you need to sample multiple completions per prompt during training, really a lot of the compute that you are spending during training is done on inference. And so efficient inference infrastructure can help you do better training. So for example, we use the VLM rollouts inference to optimize this part of the training. Also, when we try to kind of see which probabilities the LLM outputs if we use these like efficient rollouts and just vanilla rollouts, we found some discrepancies and had to really dig into rabbit holes to find those like bugs in implementation, so chase those down and make those probabilities consistent between different infrastructure variants. And also, this algorithm has a lot of hyperparameters. As usual, we had to optimize those. So for the data sets, we used as a like toy problem some mathematical problems. There are different open source data sets of varying size and varying difficulty of their problems. So one of the hyperparameters we had to tune is the temperature of the generations. It controls how like stochastic, how variable, how random each token that's just generated by LLM is. So for high temperature, you have diverse generations and maybe a lot of exploration during training. And for lower temperatures, you have a better quality of answers, but they are less diverse. And kind of unsurprisingly, if the temperature is too high, then the training just diverges. The loss starts the accuracy starts to fall. And if the temperature is too low, then on the other hand, you start with a good reward, but it doesn't really grow throughout the training. And so you need to find like this best value in the middle. Also, you have to tune the learning rate, and again, nothing really unexpected here. If the learning rate is too high, then your training can diverge, and suddenly your accuracy drops. If your learning rate is too low, then the training is very slow, and you won't get the best results. Again, you need some best value in the middle. So one of the main experiments were done with these parameters, and you can also see that we can just switch off the regularization. So in traditional reinforcement learning from human feedback, we needed the regularization because the model could kind of hack the reward model. It could produce some adversarial examples that were not good by the human judgment, but appeared good for the reward model. And for verifiable rewards, that's not really a big problem because your reward is objective. It's like, is the answer to the mathematical problem correct or not? You can still have some like misalignments. For example, if you tell your LLM that, okay, you need to pass all of these test cases in the code, it can learn to just delete those test cases. And now like there are no failing test cases because there are no test cases. But those are some like extreme cases, and generally you can switch off the regularization for the reinforcement learning with verifiable reward. So we also find that the initial checkpoint that you start with really matters. For example, if you start with a model that is already trained on some mathematical data, the starting accuracy that you can see, is quite high. It's like 64% and grows a little bit to like 68% during training. But if you start from the base model that doesn't really even know what the correct format of the answer is, the accuracy starts really low and doesn't really go really high. So this is for the Llama 8 model. And so we can kind of conclude that in the pre-training of the Llama model, it didn't really learn really well to do this like reasoning and mathematical tasks. And so even during training, we can't really increase the capabilities because there is kind of nothing to start with. And in the middle, we have the Llama 8B instruct model, and we can see a good growth from like 35% accuracy to around like 53% accuracy on the mathematical benchmarks. So some other things that we learned along the way. So yeah, again, the starting checkpoint matters. It's really good if your starting model already can do some of the like mathematical or coding tasks, already has some reasoning patterns, because they can be like increased and reinforced during the training. And if it's really, really bad to begin with, it's hard to make it good during the training. Also, we found that kind of pre-training this model on diverse difficulties of mathematical problems is beneficial. So you could think that it's like better to only train it on easy tasks or to only train it on the very hard tasks. But actually, yeah, again, the truth is in the middle, you need a diverse set of mathematical problem difficulties, and that will make the training go as well as possible. Also, again, reinforcement learning is quite unstable. It has a lot of hyperparameters, and you have to be prepared to do a lot of experiments because some of them will fail. Like, for example, some of our models just started repeating the same like thinking token, or sometimes they started just outputting infinite sequences of tokens, never stopping, and bypassing the length limit. And this is being addressed in kind of more modern papers. They also noticed that like some length regularization is probably also needed to control that. But yeah, you need to be careful with RL algorithms because they're kind of finicky and you need to get them right or otherwise the training will diverge. Also, an interesting observation is that people usually think that, okay, when you train the LLM with the verifiable rewards, it learns how to think. And so it starts thinking for longer and longer because that's useful to get the correct answer. And you can expect the length of the generations from the LLM to increase during the training. But we actually found that if you start with a model pre-trained or like SFT'd on some long already thinking traces from like some DeepSeek model or other model, then the length of the generation can actually decrease during training. So probably there is some like optimal length of the answer, and the length of the outputs of LLM will converge to this optimal value. So not necessarily it always grows during training. It can decrease if it starts from the value that is too high. And again, there are lots of rooms for improvement the GRPO algorithm and the GRPO loss formula. You can do a lot of tweaks to make it like unbiased, to make the length regularization better, and so on. Okay, so let's go to the conclusion of my talk. So reinforcement learning really helps when you want to align your LLMs with the human preferences. When you not only want to show the LLM what you want it to do, but you also want to show it like what not to do, to, for example, refuse some harmful prompts or not output some obscene language or toxic phrases. And the reinforcement learning can really help because the LLM will try different strategies during training and will get feedback and will converge to some optimal value. Also, when the LLM is allowed to do some exploration during training, like try out different, for example, reasoning strategies, it can find useful patterns, like, for example, wait, let me think about it one more time, reflecting and reiterating. And we don't need any human supervision to do that. Like, we didn't tell the model to output wait, let's think about it one more time. It just kind of holistically learned that this is a useful pattern, and because it led to correct mathematical answers, it got reinforced and kind of crystallized in the model's behavior. Also, this field of reinforcement learning from human feedback and RL for LLMs in general is evolving very fast. Like, all of those advancements are like from 2023, 2024, 2025, and I think you can expect much more, like many more new advances. For example, like new RL algorithms like GRPO, new kinds of rewards like reinforcement learning from AI feedback or from verifiable rewards, and this like new paradigm of inference time scaling. So now you not only can put a ton of compute for the pre-training of the language model, but you can also put a lot of compute to like let it think for 30 minutes and come up with a better answer on the inference side. If you're going to do the reinforcement learning in practice for your applications, you have to be prepared that it is kind of capricious and finicky, and you would need to do a lot of experiments to make it stable and not divergent. And also, as an advice, it's nice to pick the correct framework because you need to balance the like optimization power of your framework if you want to utilize a lot of GPUs with the kind of lightweightness and simplicity of the framework if you want to iterate fast, implement different algorithms, and also look out for the algorithms that are already implemented in that framework. But yeah, reinforcement learning is kind of a pain to do right and to be stable. So yeah, prepare for some technical difficulties. So yeah, I think that's all I wanted to say. Thank you for getting through this. I'm ready for your questions. Yes?
For this example, how many failed experiments did you have before the final one, approximately?
Yeah, I'm not sure. I think there was like a lot of effort put into that, like log probability discrepancies that they had to like actually debug the code before they can even run any experiments. But yeah, I'm not exactly sure on the correct number, but we probably had to do like multiple, like maybe 15, 20, 100 experiments because we needed to tune like each hyperparameter.
I have a question.
Yeah.
I'm super curious about designing actually designing reward functions when you have these verifiable outputs. So say you're asking, hey, give me the code which does that, this and that, and it might pass the test or not might pass the test, but how do you design a reward function?
To design the reward function.
Yeah, because say give me the code which outputs Fibonacci number and it doesn't pass the test, right?
Mm-hmm.
So how do you put reward functions, say, between 0 and 1? How do you design it?
Yeah, so you can do some like reward function design. Like for example, in like chess, for example, you can like approximate how well the intermediate state is of like summing the values of your pieces and subtracting the values of the opponent pieces. But actually, you don't really need to do that. There is like this post called the bitter lesson that teaches us that if you just put a lot of the compute and not really too much like human engineering, then your model will eventually train to solve your tasks. Like you don't really need to solve it for the model. Like you can probably just give it your coding problem, and if you have the correct like tests or correct answer, you can just tell it whether it passed or didn't pass. So just like either 1 or 0 reward, and you don't really have to engineer anything in between.
Sure, I think I see what you're saying.
So probably the training will be easier if you have like more frequent feedback.
Yes, absolutely.
Yeah, but ultimately, if you have a lot of compute and your model is really large, probably eventually, like AlphaGo or AlphaZero, it will train to just win the games, and you don't really need to provide any additional feedback apart from that.
Just to elaborate on that question a bit, so it's clear when you say the verifiable reward, it's like the length of the string, or is the answer correct? But is there any reward for the right thinking process? Like, for example, if you prove a theory or prove a theorem, there is there's an answer like, is it correct or not? But still, there's more steps, many steps in between that, right? So how do you verify something that's not that clear? Even in math, there is a lot of answers that they're not so clear. So how do you deal with that? Or it's just not present, it doesn't present in the data set, it's not the part of the scope.
Yeah, that's much harder. Yeah, that's a good observation that in mathematics, not all the problems are like output the correct numerical answer. Sometimes the problem is like prove this theorem. And currently, I think the current systems are not really good in it because it's hard to provide feedback. Like to check whether the proof is correct or not is much harder than to check whether a numerical answer is correct or not. And so, yeah, in theory, again, you could like collect those reasoning traces and try to distinguish between like correct traces and incorrect traces. Maybe you could do some like SFT on good reasoning examples, but that's all expensive. And I think the hope is that, again, like the model will just learn itself how it needs to reason to arrive at the correct answer. So yeah, I think you can expect more progress for the problems where you have this like easy verifiable rewards, like is this correct or not, and not when you have to check the intermediate process. But maybe eventually it will generalize to that as well.
It's like a relatively small model. Was it done intentionally as like a toy example, or you're indeed using that in production?
No, that's more of like a toy example to play with this algorithm and to make the infrastructure right, and then to move on to the bigger models.
Okay. Thank you.
Yes?
I'm curious about the regularization.
Mm-hmm.
You mentioned, Kyle, divergence to prevent model from, yeah, this slide please, to prevent model from making adversarial attacks on robot models.
Mm-hmm.
So what new policy optimization, I see that divergence is calculated differently, and I'm unsure what it meant to describe.
You mean that like here it goes in the reward and here it goes directly to the policy model?
Yeah.
I didn't describe it, but there are, I guess, like multiple ways. You can either like add this penalty to the reward and use it in your reinforcement learning algorithm, or you can put it directly into the loss function and to optimize it directly. So I think in GRPO they found that it's better to put it directly in the loss function. Yeah.
Were you using only constant temperature, or did you consider any dynamic temperature strategies?
I think for now we only used constant temperatures.
Constant, and all those plots for accuracy are with constant temperature.
Yeah, I think like they used one temperature for training to encourage diversity, and then a fixed temperature for the inference, like a lower temperature to get more high quality answers. Yeah, there was.
Is there any example other than coding math and maybe formatting in production where verifiable rewards work?
Yeah, I think you can look at the examples like Alpha Evolve. They try like different, I guess, setups when you can have something that is can be measured, and they optimize like some like matrix multiplication algorithms to multiply matrices in the least amount of computations. Also, in like Perplexity, we really want our models like not to hallucinate. And sometimes you have an answer and you have some like ground truth knowledge from like some database, for example, and you can check if the answer is factually correct if you have some reference answer. This is more fuzzy and less like objective, but I think also can be viewed as kind of a verifiable reward.
Thank you very much.
Thank you.